Hey guys, welcome back to EduMoon tutorials on database management systems. This is Vidya, and in today's lecture we're going to discuss the properties of decomposition. So as we know what decomposition is, we have seen what decomposition is and why we actually use decomposition in our previous lectures. So in this video we're going to concentrate on two different very important properties, or you can say aspects of decomposing a particular table. So we do all of these things to eliminate the redundancy and also maintain the data consistency. But in this part, we'll concentrate more on the redundancy part of data. So what we do usually, we'll take a large table which has some redundant information, and then we'll try to reduce the redundancy by decomposing that particular large instance of table into smaller tables. At that point of time, we'll decide whether to decompose a table or not by considering the normal forms and the functional dependencies that we have seen and discussed in our previous lectures. So once we have decided to decompose a particular table, then we have to consider two questions. You have to consider two things. First question is that, can we recover the original instance from the smaller instances that we have created or not? Can we revert back the process of decomposition back to the original table ostunda rada? Second question is that, does it allow us to check the integrity constraints efficiently or not? So this is to let us know if we can check the integrity constraints efficiently or not. So these are the two questions that we have to pay attention to when we decide to decompose a particular instance into smaller instances. Like we have the normalization and the functional dependencies that actually guide us in taking the decision of decomposing a table or not. We have some guidance to help us with these questions also. We have two properties of decomposition that will guide us to find answers to these questions. So let's look at those two properties of decomposition. The first property is that lossless join decomposition. Let's look at what lossless join decomposition is. As the name suggests, lossless join, that says when you are decomposing a particular table instance into smaller instances, you will also be able to get the original instance when you actually perform the join operation of these both newly decomposed relations. Ante, when you're dividing the table into two instances, now when you combine those back, you will get the original instance that you before decomposition. Right. So that is what is lossless. మీరు డికంపోజ్ చేశారు, then when you're combining them, మీకు ఎక్కడ లాస్ ఆఫ్ ఇన్ఫర్మేషన్ అనేది ఉండదు అనమాట. So that is what is lossless join decomposition. Let's look at the definitive form of defining lossless join decomposition. Let R be a relational schema and let F be a set of FDs. Over the R, a decomposition of R into two relations with the attribute sets X and Y is said to be a lossless decomposition with respect to F if for every instance R of capital R that satisfies the dependency in the capital F. So what is this? First, the projection of X columns in that particular instance combined with, or the join with the projection of Y columns in that particular instance will give you the original instance. Projection of X of that particular instance join with the projection of Y attributes of that particular instance will give you the actual instance. So this is how we can symbolize this lossless join. So when you are combining, you will get the actual instance without loss of any information. So yeah, decomposition can be lossy also, but in order to eliminate the redundancy, we have to use the lossless join only. Lossless join is a must if you want to reduce or eliminate the redundancy, right? So we have a small test to check if this is a lossy or a lossless decomposition. What is that test? That is according to the Theorem 3. Let's discuss what Theorem 3 is. Let R be a relation, F be a set of FDs that hold over capital R, which is relation. Decomposition of R into the relations with attribute sets R1 and R2 is lossless if and only if F closure, that is F plus, contains either the FD, that is R1 intersection R2 determines R1, or FD R1 intersection R2 determines R2. right? We can say a particular relation is lossless if the f dash contains the fd's which are common in both the relations that actually determines one of the relation, that is, it can be R1 or it can be R2. Let's understand it clearly. Right. Let's take an example. We have a hourly employees example, and this is the instance that we use for depicting this particular relational schema. S is the sailors, ID, N is the name, L is the boat or something, and R is used for rating, W for wages, and H for hours worked. So this particular in relational schema is divided into two instances because we have seen in a previous example where wages is completely depend upon the rating, and we'll have duplicate information of rating with the wages. So we have decomposed that particular instance into two smaller instances, one with the rating and wages and the other one with the remaining elements or attributes that are present. So here, like we said, this will become R1 now, and this is R2. So this should have the functional dependencies R1 intersection R2. What is the common thing in both the relations? Of course, R. R is a common thing. The first one is done. It should determine either R1 or R2. It is determining. See, R determines W, it holds. So this decomposition is a lossless decomposition. So when you combine these two instances that you have decomposed, no information will be lost. You can actually retain the original instance, which is SNL RWH, right? So this is a small test that you can perform to check whether the decomposition is a lossy decomposition or a lossless decomposition, right? So this is all about the lossless join. Let's look at the second property, which is dependency preserving decomposition, right? Okay. Let's start this with an example. I can say, but let us consider an example, then you can understand it better. We have a contract. We have seen this contract example also. What is an instance that is used for symbolizing this? CSJDPQV, right? So, and FDS. What are the FDs that are present? We have three FDs, right? We have considered the known FDs, which are C determines the entire relational schema, and JP determines C, and SD determines P. I have explained these functional dependencies in the functional dependency lecture we have discussed. So I recommend you to watch that particular video so that you can understand what these are, how we have known all of that. Right. So as SD is not a key dependency, here of course SD determines P is not a key dependency. So this of course violates the BCNF, where every key and non-key attribute should completely depend upon the original key attribute, and this has to be either a super key or a candidate. So once you have decomposed this table into two relations with STP and the other one having all the other attributes like C, S, J, D, Q, V, this is a lossless join because when you combine, you don't lose any information. But when you try to insert some data, you should consider the functional dependencies that particular table has. In order to check those integrity constraints and those dependencies, you have to combine those. How can you combine? You have to perform the join operation, but this join operation is an expensive join operation. Each time when you insert, you have to perform this join operation. Of course, this becomes expensive. So this type of decomposition is known as the not dependency preserving decomposition, because in order to preserve the dependency, you have to perform an expensive join. So this is not preserving your dependency. So for that, you have a solution for using. You have another property which is called dependency preserving decomposition, which allows you to check only one instance. In order to check for the integrity constraints, you can only consider one relation and division చేసాం కదా, ఇప్పుడు ఒక్క రిలేషన్ లో చెక్ చేస్తే చాలు, రెండో రిలేషన్ లో కూడా చెక్ చేయాల్సిన అవసరం లేదు. How can you do that? You can perform the check in one relation and the check in another relation. ఆ రెండు చెక్స్ యొక్క రిజల్ట్స్ మనం కలపొచ్చు అన్నమాట. That is called the projection of FDs, right? Let's look at what projection of FDs. First, I'll tell you what it is, then we'll see the definitive explanation of what it is. Projection of FDs is nothing but first you will project the X attributes into the first relation and you will check the integrity constraints. You will obtain a result. You will combine this result with by projecting the Y attributes in the second relation and you will check the integrity constraints. Now you will combine both of them, you will perform the union. This gives you the actual functional dependency set of the original instance. Okay, so let's look at the definition that we have in our textbook. So let R be a relational schema that is decomposed into two schemas with the attribute sets X and Y, and let F be the set of functional dependencies over the particular relation R. So the projection of the function F on X is a subset of the functional dependencies in the closure F dash, that is involve only in the attributes in X. We denote this as Fx. So what is Fx? Projecting the FDs in the closure onto the attributes in the X is symbolized as Fx. A dependency that U determines V in F closure is in Fx the decomposition of the relational schema R with the FDs F into schemas with attribute sets X and Y is dependency preserving if and only if this condition satisfies. So what is it? First project the X attributes in the first relation instance, check the integrity constraints, and then do the same with the Y attributes in the second instance. Now you perform the union of both of them, you will get the actual functional dependency set of the original table that we have considered. We know what F dash is. F dash is a set of functional dependencies that are implied on that particular relation. So you're getting that by performing the separate F checks on the X attributes and F checks on the Y attributes. Now this is the dependency preserving join, right? So guys, these are the two important properties of a decomposition. So yeah, this is it for today. I'll meet you in the next lecture where we'll be discussing probably the last topic of 4th chapter. Till then, stay tuned. Thank you.